and recording. I am sharing my screen, I believe. Let's just double check that. Allow. And I am still recording. Good, excellent. And not unmute, excellent. Okay. Come back here. All right, real quick, we will go over what the answers to the quiz are, satisfy all of your curiosity. On number one right here, this is a simplification problem for big O notation. You could have used the repeal to the limits and definitions. You didn't need to, though, and you had almost this exact same problem, just with some different numbers in front of the A's and B's on your notes here. But again, the purpose or the idea of big O notation, the reason we use it, or any of this asymptotic notation, the reason we use it is so that we can take complicated expressions like this. They don't have to represent runtime. They just are some complicated expression for a function, and we can simplify it to the most important parts of that expression. And in this case, when we're simplifying all of these smaller, somehow smaller terms, like this a is smaller than a squared b, they all go away. And the only final terms that we have left over are this a squared b and ab squared, and we can get rid of the constants. And so this is in fact true, that this whole big long thing over here is also equivalent to this thing over here. And the thing on the right, much more convenient to work with and understand. So that's what we will be using throughout this course all the time, simplifying these big, long expressions into something simpler. So number one here was true. Number two is asking about the fastest possible algorithm for computing the matrix multiplication, matrix product A times B. And we don't know what the fastest possible algorithm is. We only have bounds on what the fastest possible algorithm. We only have bounds on its runtime. And the lower bound that we have is omega of n squared log n. N squared here is less than that lower bound. So we know that this it is impossible to do matrix multiplication in time O of n squared, no matter what algorithm you might possibly use in the future. And so this is false here for number two. Number three, this is one of the problems from the last portion of your notes packet, was asking you to actually compute the runtime of doing this, this expression right here. Now we're not actually computing it, you're just verifying if this expression over here satisfies the runtime. And again, we have a matrix multiplication of an A times this whole thing right here will be another matrix after we do that inversion. And we know that that must take time at least n squared log n, and so again this must be false because it's for the same reason up here, is that it's another matrix multiplication. So this answer right here was false. And the actual problem on the notes packet, that you computed the runtime of this, we think of this runtime as O of n cubed, as cubic, for two reasons. One, it has an inverse inside of it, and we think of the inverse as cubic. And the second is that it has two matrix multiplications inside of it, and we often think of matrix multiplication as cubic. But the best possible runtime of those things, we don't know what it is. We just know that it is at least n squared log n, and so it cannot be O of n squared. So that's why this was false. Last problem, number four, down here, there's another expression right here from the notes packet. And here there is a bunch of the BLAST level 2 or 1 operations going on, like scalar multiplication and addition. And then here, this whole thing is a matrix times a vector, and then a matrix times, or then a vector. This, my highlighting won't let me get just that one X. So that whole thing is going to be a vector times another vector. And this Frobenius norm down here at the bottom, all of that happens faster than cubic, happens in time n squared, because there's no like matrix operations going on here. So there's nothing that is going to be cubic or at best n squared log n. Everything happens in n squared time, and in fact it is theta of n squared as well as O of n squared. So this number 4 was true. If you have any questions about any of those problems, then I'm happy to take those after, go for it right now. Yes.
Sorry, you said it's theta of n squared?
So this expression can be, the best way to compute this expression, best possible formula for computing this expression, does have runtime of theta of n squared. Yeah.
So why would you say true for theta?
So the question is, if it's theta of n squared, then why are we saying true for O of n squared? And the definition of theta is that it is both O and omega. So when we say something is O of n squared, we are not saying that it is not theta of n squared. We are not saying that this is the best possible thing. We are just saying that this is, in fact, an upper bound on something. And so it is possible for something to be both O of n squared and theta of n squared at the same time. So this O here is not an exclusive situation. Similarly, if it said omega, that's not exclusive. This problem right here would be true, whether this was O or theta or omega right here. All three of those statements would be true.
So for future answers, that the correct answer is theta, and the question says big O or omega, then it's almost.
Yeah, theta implies O or omega. O by itself does not necessarily imply theta, and omega by itself does not imply theta, but O and omega imply theta. Good question. Today in class, we're going to go over, let's come back over here to our class repository here for a second, and we're going to be going over this topic 1 here. Before we do that, though, I want to highlight a GitHub issue posted today. So again, if you have questions in this class about something technical or administrative, really about anything, the right thing to do is to ask those questions on GitHub issues over here. And so there's an excellent question over here on GitHub issues that shows the overview of how to do something like that. This is just asking about one of the problems on the quiz, and provided the answer down here. But I want to remind you all about why we're doing this, posting to GitHub issues, and 2 big reasons. The first reason is that by posting to GitHub issues, instead of, for example, emailing me, it means that everybody has the your question and the answer response available to them. It also means that maybe like I'm not available for a little bit for whatever reason, that I don't just live on GitHub checking GitHub issues. But I do check those much more than email. But for whatever reason, if I do not see this issue right away, somebody else might see it and provide an answer before I'm able to do it. And the last reason is that when you are applying for jobs somewhere, one of the things that recruiters look at is your GitHub profile. And one of the things that they look at is the various statistics, like how many GitHub issues do you have, how many times do people reply to your GitHub issues, things like that. And so we're, in some sense, like hacking the recruiting process of these corporations. I'm trying to inflate your GitHub profile scores here. Today in class, we're going to be talking about the mathematics of PageRank, starting with that, and eventually, probably in 1 or 2 class sessions, we'll see how PageRank is actually used in GitHub to rank various programmers. And so it will be used to rank you when you are applying for jobs. And we want to inflate your GitHub PageRank so that you are looking better to potential future employers. So long, complicated thing just to say post questions on GitHub issues. Today, we're in the topic 1 computation PageRank folder. And I've also added this notes2.pdf file here. So if you are doing things electronically, then you will probably, I think, get to this file today. So you'll want to have access to that file. This notes1.pdf, though, I passed that out physical copies last time. And we'll start with the notes1.pdf today, and then possibly get to this notes2.pdf. If you want a physical copy, there are physical copies of the notes2.pdf here up front. Before we get into the technical thing, though, for today, one last announcement, and that's posted here at the bottom. There will be another quiz next class period this coming Wednesday, and it will be the first problem from the notes. So coming over to here, PageRank 1, the quiz will be, I will just print out this page exactly as it is in the notes. This page right here and this page right here, this problem 1. And your responsibility will be to provide all of these definitions. For example, for an irreducible matrix or a primitive matrix or an aperiodic Markov chain, just writing them out from memory. This next quiz will be a closed note, no computer quiz. So you really do have to actually memorize all of these definitions. Why am I making you memorize things? It's because we're going to be doing a lot of different math problems related to these definitions. And if you don't actually have the definitions memorized, you just can't do the math problems. So many times I work with students on math related classes like this, and students struggle with the problems, even the problems that are intended to be easier problems, because they just don't have these definitions memorized. So memorize those definitions. I want to force you to memorize those definitions. That's the purpose of this quiz on Wednesday. I realize it's a short turnaround time for doing another quiz. But again, the reason for this is because we can't, like, you will just not be productive in class working on these problems if you don't have these definitions memorized. Again, last time I asked you to, before class today, to complete the section 1, the background, and the definitions on notes 1.pdf. So that was asking you to complete these problems. So you should have, if you've been doing this, already exposure to these definitions, and now you just need to sit down and memorize them over the next couple days. Like this quiz, today you'll have the first 10 minutes in class. Plus, if you'd like to arrive early, I'll be here at least 10 minutes early for you to start the quiz early. I've also this time provided my definitions here in the quiz-key.pdf file inside of this folder, so you can take a look at what those look like. Where is it? My definitions are just a scanned copy of handwritten definitions. And again, all of these definitions appear exactly word for word inside of the reference material for this week. But if you want to see exactly how I wrote it out, then you're welcome to do that. On the quiz itself, I'm asking you to memorize these definitions. Your whatever you provide does not have to be word for word what I have here. It just has to be mathematically equivalent to what I have here. So it doesn't have to be word for word, just has to be mathematically mean the same thing. Oops, so it looks like I wrote here, let's refresh this page, -2 points for each incorrect definition that was wrong. It should be -1 point. Where did it go? -1 point for each incorrect definition here. You won't be able to go negative on this quiz. So 0 out of 4 is the worst possible score that you could get. But there's, I don't know, like 7 or 8 definitions or so. Any questions about anything administrative in this class or what to do for the quiz on Wednesday? Okay. Today in class then, we will start going over this notes packet and thinking about reviewing in our head some of these definitions here. So coming down here, this problem 2, more definitions right here. These problem 2 definitions will not be on the quiz, but these are things that just having a general sense of will help you with understanding of the paper and the material that we'll be talking about in class. So you definitely want to have that done. And now problem 3 right here, what I'm calling these trivial problems. And trivial problems in a mathematical sense are problems that the answer comes directly from the definitions. Let's zoom in on here. There we go. The answer to these problems comes directly from these definitions. And so if you have an understanding, a good understanding of these trivial problems or of the definitions, then these trivial problems will be relatively easy to solve. Not super easy. It might take you, I don't know, a half hour to solve one of these problems, but solving a problem in a half hour is still something that mathematicians think of as a trivial amount of time. It's not like a month to solve one of these problems, which would be an example of a non-trivial problem. Okay, problem number 3 here, a stochastic matrix. Let's all of this is asking us to provide an example of these different definitions here, giving us some practice with working with these definitions. Okay, so a stochastic matrix, again, is one where all of the rows sum up to 1. So there are many possible examples of a stochastic matrix that you could give. The simplest example of a stochastic matrix would be a matrix with just 1 row and 1 column, where the entry here is 1. A more complicated, larger one might be the identity matrix, 1, 1, 1. Here I'm writing out in 3 by 3. But there are other possible 1, 1, 1 over here. These are all examples of stochastic matrices. Another way that I might write a stochastic matrix sometimes is putting a constant out in front, like 1/3, and then 1, 1, 1, 1, 1, 1, 1. like this. And now if you do the multiplication of 1/3, the constant scalar multiplication times a matrix over here, each one of these entries will be equal to 1/3. And so if you sum up all of those rows, each one of those rows will sum up to 1. For a problem like this, like just literally to solve the problem, all you need to do is provide one of these. But it's good to have like a handful of examples for all of these definitions that you can think about when we're solving more complex, less trivial problems. Are there any questions about what a stochastic matrix is? Say that again. Question is, do stochastic matrices have to be square? And the answer is no, that all the examples that I provided here are in fact square. We could provide another example here, something like that, where it's very non-square, it's basically a vector. And that still satisfies the definition that every row sums up to 1. For the purposes of the pagerank algorithm, though, all the pagerank stuff, all the examples we will see, all examples that we will see will be square. I think even all the matrices that we'll be working with in the pagerank stuff happen to be square. Good question. Any other questions so far? Okay. A non-stochastic matrix is just any matrix where the rows don't sum to 1. Very easy to come up with. So 0 matrix, 1 entry, maybe the put a 4 up here, 0, 0, 1, like this. One of these rows sums up to 1, but the other one does not. So that's non-stochastic. We have 1s everywhere without the scalar multiplication out front, also non-stochastic. And stochastics, non-stochastic, doesn't say anything about the shape of the matrix. So if we had, say, like 0, 1, 0 here, that would also be non-stochastic. Any questions about that? Okay. There are a lot of definitions in this first set of notes, a lot of definitions in this PageRank paper. And this is one of the simpler ones, but you will have to have all of these definitions very, very much down pat again in order to be able to solve simple problems like this and the more complicated problems we'll get to later on. Okay, next example here. This is a definition actually from your quiz that you'll have on Wednesday in irreducible matrix. One good way of studying for the quiz, besides just memorizing the definitions, is also to work through all of this note packet here and make sure that you can provide examples or counterexamples for all of those definitions. So an irreducible matrix here, let's go check out what is the definition of an irreducible matrix. And the paper gives a very informal definition here of an irreducible matrix. It says the graph shows that every node is reachable from every other node. Very informal definition. There are many more formal definitions that require more complicated techniques to understand what's going on. If you've seen those before, you're welcome to provide them, write them, but you're not required to. This is the definition from the paper, and so this is what we'll rely on for the class. And so let's talk about what exactly does this mean. The graph shows that every node is reachable from every other node. Coming back over here, ultimately in PageRank, we're going to be seeing examples of directed graphs. And the classic example of what these directed graphs represent is web pages. And so let's say we have 3 web pages. I'll call them 1, 2, and 3. Each one of these web pages being a node in the graph. And then we have links between these nodes, directed edges between these nodes, if a web page references another web page. So if web page 1 here references 2, we might have a link like that. And if 2 references 3 like this, then we would have a link like that. This graph representation right here, this is equivalent I'll use a triple equal sign to talk about equivalency between different types of objects. So a triple equal sign, this thing on the left is equivalent to a 3x3 matrix. 3x3 matrix, where we have a 0. Let's see, I'll label these columns 1, 2, 3, 1, 2, 3, where the rows right here represent the sources of links, and the columns represent the targets of links. And so on node 1 right here, there's an edge over here to 2, and so we could have a 1 right there. And then node 2 has an edge over 3. Node 2 has an edge over to 3. So we'll have a 1 right there, and then zeros everywhere else because there's no links between these other nodes. And I'm saying these two things are equivalent because there is an obvious sort of transformation about how to go from the graph to the matrix, or from the matrix over here to the graph. This is, I think, a straightforward-ish example here. A straightforward-ish example. We're going to make the example a little bit more complicated. I'll do it in red down here with these same numbers, but add a few more edges, like this, and add these same original links, but then we'll add some more links to our graph here. I'll say 2 can also go back to 1, and 3 can also go to 1 like that. And we'll add also here that 3 can go back to itself. So there's a self loop going back to itself. Written out in matrix form, this would look something like, I'll write the columns here just for convenience, but it's not required. The 1 over here, the source, has no link to itself. It does have a link to 2, does not have a link to 3, so it would look like that. The 2 over here goes to both 1 and 3. The 2 over here goes to 1 and 3, so 1 in both of those 2 columns. And the 3 over here goes to 1 and back to itself. So the 3 goes to 1 and back to itself like that, and does not go to 2. This would be one way of representing this this graph as a matrix. An equivalent way of representing this graph as a matrix, it would be also to divide these numbers by 2 right here, divided by 2, divided by 2, divided by 2, divided by 2. And we have a 0. In this case, implies no link, and a non-zero implies a link. And I'm dividing by 2 here so that the matrix becomes stochastic. Either of these representations is in some sense equivalent. The stochastic version of this representation, though, is what the paper is using when they are doing these conversions between graphs into matrix forms. Okay, I'll pause here. I see some hands for questions. I'll go back to front. Yes?
Yeah, so just to confirm, the top one is still a irreducible matrix?
Yeah, so there's a good question. The question is that at this point, I've totally ignored this, like, what is an irreducible matrix? And I'm just providing examples of, in the definition right here, about how to interpret this idea of the graph shows that every node is reachable from every other node. And the question is, now let's think about the irreducibility of matrices, and are these irreducible or not irreducible? In this first problem up here, so the question is, can every node get to every other node? And if we start at 3, for example, over here, we cannot get to 1 or 2. Or if we start at 2 over here, we can get to 3, but we cannot get to 1. So this is not irreducible right here, not irreducible. But down here, this more complicated graph, no matter where we start, we can get to every other node. And so this one is, in fact, reducible right here. To me, it's a little bit confusing. I get tripped up oftentimes about the reducibility or the irreducibility and getting those backwards. That my intuition is that something should be reducible if it goes everywhere, but that's the opposite. Something is irreducible if the graph shows that you can get from any one location to every other location. So irreducibility implies you can go everywhere. Then reducibility implies you can only get somewhere. So maybe I'll draw a little arrow that this is really an example of the reducible matrix right here. Good question. Other questions? Yeah. Sorry, what's your name again?
Yeah.
Jay. Yeah.
Why doesn't each node also need to get back to itself for reducibility?
Question is, does each node need to get back to itself for reducibility? And the answer is that it does need to get back to itself, but it doesn't matter how long it takes to get back to itself. So here, if we have, say, node 3 right here, it has this self loop, so it can immediately get back to itself. But node 1, in contrast, does not have a self loop, and so it cannot get back to itself right away. But one can still get back to itself after many, many hops. We go from 1 to 2, and then 2 to 3, and 3 back to 1. So even though there's no self loop right here, we can still sort of go around in a big awkward circle and get back to ourselves. So irreducibility doesn't talk about how long it takes to get back to yourself. It's just saying that if you follow these arrows forever, making random choices, eventually you could get back to yourself. Good question. Okay.
What is the meaning of the self loop within the context of web pages?
The question is, if we had a web page, what is the meaning of a self loop like this? And the answer is that the web page links back to itself. And this is actually a very common thing to happen on web pages. So if you take any major newspaper, like the New York Times, for example, at the top somewhere, there's going to be a button where if you click it, you go back to newyorktimes.com. So it's very common on web pages to have links that go back to the web page that you're currently at. And so it's actually relatively common in the web graph to have these self loops. Good question. Arsh first. Yeah, so we could have, the question is, what about negative entries? And maybe an implicit thing that I did not say here with stochastic matrices is that the stochastic matrices has to be non-negative, so between 0 and 1 values. You can't have a negative entry in your stochastic matrix. And in general, all the matrices that we'll be working with related to PageRank are all going to be non-negative matrices. So for a web graph, for example, it wouldn't make sense to have a negative sign in any of these spots. So that's not something that we'll have to deal with. So the question is on the definitions, how important is it to talk about like the non-negativity of things? And the answer is, for the purposes of this section of our class, you can just assume that matrices are non-negative without actually specifying that. One of the weird sort of things for beginning mathematicians about mathematics is that you're brought up thinking that like mathematics is this clear, crystal cut thing with correct answers and not correct answers. But it turns out mathematicians don't actually practice math in that way, that we have lots of unstated assumptions all throughout our work that we're doing. And here is a great example of an unstated assumption that I had about things being non-negative everywhere in these matrices. Another example of a non-stated assumption I have is that these matrices are real valued and not complex valued. And in general, throughout this class, there will be lots of times where I maybe accidentally don't state some of these assumptions. And so it's a great question to get those clarified. Yes, good questions. Go ahead.
I was just asking this one. And that's to convert it into stochastic.
The question is, this pink stuff over here on the right, why do we have this pink stuff over here on the right? And the answer is to make it a stochastic matrix as well as the irreducible matrix, yes.
What do you mean by no link?
The question is, what do I mean by no link and link over here? And the answer is that the link are these directed edges between the nodes. And so if there's a 0 in the corresponding entry here, it means there is no link, no directed edge between those nodes. And any non-zero value, or maybe more precisely, any value between 0 and 1, means that there is a directed edge in that location. Angela.
So can you just do whatever like operation you want and make a non-stochastic matrix a stochastic matrix?
The question is, can you do whatever operation you want to make a non-stochastic matrix a stochastic matrix? And the answer is, in some sense, yes, that, and in some sense, no. That it's always very problem dependent. Here, this stuff that I'm writing out in pink here is the way that it's problem dependent is that this is just something that the paper that we're reading happens to do. It's not something that is required that you do in general when you're working with these graphs. It's just something that the paper happens to do. And there are other things that you could do as well. You could make everything sum to 10 if you wanted. You could do lots of different other things that you might do for different applications. So in general, like this is, there's lots of different things you could do, but for our particular problems, for the purpose of this course, this paper that we're reading, this is the thing that that they do, and so that's the thing that we will continue to do. Good questions. I'm going to pause to our discussion here to go over to the paper and highlight where all of this information can be found in the paper so that you can review that. Coming over here, this is the paper again, the Deeper Inside PageRank paper. I've already asked you to read through this and find those definitions. But I also was a lazy, arrogant undergrad at one point, and I realized that most of you probably have not done that because I would not have done that because, again, I was lazy and arrogant. And so it's okay with me if you guys are as well. Section 3.1 down here, this is where they are explaining their basic PageRank model, how they're representing these graphs and converting them into matrices. So they have this example right here of the different computations and things that they do. And so, yes, if you haven't read through that, read through that. And this is the reference for what we're doing right now. Good questions so far. Any other questions so far? Okay. So the remainder of this section of problems, problem 3, all is related to these definitions and that section 3.1. Go ahead and write that out right here. Everything from section 3.1. And so I will let you do this same exercise with primitive matrices. Going through that section 3.1, they provide explicit examples of primitive and non-primitive matrices. You should be able to come up with your own similar, maybe simpler examples. And is not required to do this for the upcoming quiz because the upcoming quiz is only memorization. But if you do this, it will make memorizing the definitions easier because you all have a sense of why things are defined the way they are. So section 3.1 for that. Problem 4 is similar, except there are some concrete specific matrices, and they do mention these in section 3.1, this P bar and P bar bar matrix. And it's very important to understand whether those are stochastic, irreducible, and primitive. So I'll also have you go through section 3.1 again and work on this problem by yourself. Again, those problems will not be directly on your quiz on Wednesday, but they will really help you understand why the definitions are the way they are. And you will be tested on these problems more directly later on. So I recommend doing this as part of your studying for the quiz on Wednesday. Any questions on those, what to do? Yes, go ahead.
Looking at the NCP, I just got a question on your writing. It looks like you meant to put rows, but it looks like it says roos.
I probably have typos everywhere.
No, it's on the handwriting.
Yeah, I probably have handwritten typos everywhere.
Okay. Just want to check because I don't want to write the wrong word. It looks like it says roos, and your W in the next word looks like that.
My W and my O's often look similar to each other.
Yeah.
This right here, yes, this is definitely a W right there and not a U, despite what you might think. This is also definitely a W and not a U, despite what you might think. And you might even think this is an O, but that would be a complete mistake. Yeah. So this is actually how I write my W's. Long story short is that this distinguishes them from omegas, and so is how I have come to write them. Yes, good question. Actually, in general, I'm very proud of my handwriting on whiteboards, but I'm not going to be writing on the whiteboard ever. And I'm very embarrassed about my handwriting on this little tablet-y thing because it's so small and awkward and cramped. So I apologize about any handwriting issues. But good question. Where were we? Problem 5. So we'll do some problem 5 stuff here. The definitions here in problem 5 are not related directly to most of the definitions on the quiz in terms of like actual mathematical definitions like the reducibility, irreducibility, primitivity, non-primitivity, but instead they're asking you to understand properties of these 3 special matrices, P, P bar, and P bar bar, that we will be using throughout the next couple class sessions. And again, these P, P bar, they are on your quiz, understanding what these P, P bar, and P bar bar matrices are. So you will have to have those memorized for the quiz. Let's see. Yeah, we got time, so I'll do this first problem right here of the rank of P bar bar is equal to 1. So the rank, if you don't remember from your linear algebra class, actually all of this problem 5 is intended to review different like linear algebra definitions like ranks and eigenvectors, eigenvalues, help review those for you so that you will be able to use those very effectively on our next problem sets. But so what is the rank here? The rank has many equivalent definitions. One of them is the number of linearly independent rows or columns. There, I've made my W have a little bit of a dent in it to be easier to read. Number of linearly independent rows or columns, and those are always guaranteed to be the same number. It's the column rank versus the row rank of a matrix. Also, the number of non-zero eigenvalues of your square matrices. Number of non-zero eigenvalues. And there's a handful of other equivalent definitions that may or may not come up in this class. But these are definitely 2 very important ones and things that you should definitely know about the rank. Some quick properties of the rank that you should also know is that the rank is always at least 0. And here, if P is a n by n matrix, which it is by definition, so P bar bar being n by n implies that the rank is at most, rank is less than or equal to n, at most n. And this particular question here is asking about this P bar bar matrix and the rank of this P bar bar matrix. All of the previous stuff, problems 4 and up, are explicitly stated. The answers to those are explicitly stated in the reading. Problem 5 here and below, the answers are not specifically stated in the reading. So problems below this mark, not explicitly, that is a L and a Y merged together in one. It's called, there's a fancy name for that in typography that is skipping my mind right now. Problems below, not explicitly in reading. But it's just the sort of thing that the authors of machine learning data mining papers like the one that we're reading are expecting will just be obvious to whoever the reader is. And so the authors will assume the consequences of all of these problems without actually telling you something like the rank of p bar bar is equal to 1, or that it's equal to whatever it is. They're just expecting that that's obvious to the reader. So these sort of problems right here, 5 and below, intended to help you practice, get used to doing these sorts of things for yourself so that you can understand what should be obvious. Okay. So let's actually work through this problem. Lots of preludings to start working through this problem. So in order to answer this problem, we're going to need to understand the p bar bar matrix. And coming back over to our definitions, p bar bar is defined in terms of p bar. P bar is defined in terms of p. So there are 3 matrices, all very closely related to each other. And again, it'll be very important for you to understand how these 3 different matrices relate to each other and what the different properties are of these 3 different matrices. Again, understanding, having those definitions memorized will be critical in order to be able to do a problem like this even moderately efficiently. So because p bar bar depends on p, we will start with talking about what is the p matrix. The p matrix is the matrix that we were sort of looking at above, that is the raw like web graph matrix. Raw web graph matrix. In the and so in the notes up above, the matrices that I actually wrote out explicitly when we were looking at the web graphs, that is an example of the p matrix. Maybe I'll just come up here really quickly and make that explicit and say that this right here is equal to p, or this right here is equal to p. Coming down there. But we saw before that the p matrix does not necessarily have to have all the nice properties that we might want it to have, like being stochastic. That a p matrix could have a set of rows that is all zeros if there are no links between the rows. And so what p bar does is it makes the p matrix stochastic somehow. So let's do an example to see how it is doing this. So my example p matrix will be, what's this thing? Okay. P equals, we'll do a 3 by 3 matrix of 1, 0, 0, 0, 0, 0, 0, 0, 0. This matrix right here corresponds to the web graph. I'll draw that out right here. 1, 2, 3, and I'll write the little equivalence symbol right here. The web graph where 1 is linking back to itself, and there's no connections between, say, any of the other nodes to themselves or to the other nodes. This is a valid graph, a valid web graph. This sort of thing does come up in many locations on the internet where you have something that links back to itself, but nothing else links to anything else. And we want, one of the things that we will see is we want our matrix that we're going to be working with to be stochastic. And so the purpose of p bar is to somehow fix this matrix to make it stochastic. And we do that by adding some values to these empty rows over here. And I'll say, so the p bar bar example from this above, the rows that are already stochastic don't get modified at all, so that is still 1, 0, 0, stays as 1, 0, 0. But these stochastic rows, we add, these non-stochastic rows, these rows that are all zeros, we change those zeros into something else so that it becomes stochastic. And the paper talks about why you might want to do different things, but the sort of default obvious thing to do is to just make it the same everywhere. In this case, it's a 3 by 3 matrix, so it's 1/3 everywhere, 1/3, 1/3, 1/3, like so. And And that's how we go from P to P bar. Yes, question, Kate.
So when you change P to bar, does it change anything in the actual nodes for all of the fractions?
Yeah, so the question is, when we change from P to P bar, does it actually change anything about the nodes themselves or the underlying graph? And the answer is that there is a graph corresponding to P, which is this graph, and there's a different graph that corresponds to P bar, and it will look different. Let's go ahead and draw that out. I will go downwards so that there's space. That's equivalent to 1, 2, and 3. The 1 still going to itself and to nothing else, but now the 2 links to 1 to itself and to 3. So we have this, this, and this. The 3 links to 1 and 2, 1 and 2, and to itself. And so the graph that corresponds to this P bar matrix is in fact different than the graph that corresponds to the P matrix up here. Good question. In this example here, the graph that we have here from P bar is a non-irreducible graph or a reducible graph because not every node can get to every other node. That if we're at this one spot right here, there's no way we can get to any of the other nodes because 1 only goes to itself, doesn't go to either 2 or 3. And so the purpose of this P bar matrix is to P bar to make P bar irreducible. And I'll pause that for a second. I saw a hand up over here.
When you made the P bar and changed P, could you have just made like 1 0 to 1 in the second column?
The question is there a different way that I could have made this P bar from this P matrix in order to get this property of being stochastic? And the answer is yes. There are many different ways, in some sense, an infinite number of ways of constructing a stochastic matrix from a non-stochastic matrix. Some of the details of especially the later parts of the paper talk about why you might want to do something that is different than this like even split between everything. But for our purposes, P bar is defined this way where this is the construction it uses, where everything is sort of spread equally. Yeah. So good question. This is the right sort of question to be thinking about like, are there, like P bar has this desirable property. Are there other ways that I can get this desirable property? That's the exact right way to be thinking. But for the way P bar is actually defined, it's defined by modifying these rows this way. Good question. Okay, P bar again, making P bar irreducible. There's a formula for that. This formula right here. The P bar equals alpha P bar plus 1 minus alpha E transpose over N. And it might not be obvious to you what exactly that means. That's okay if it's not obvious to you what that means. But I'm going to make you read and try to understand that in the paper and not talk about it exactly right now. Well, actually, let's go ahead and talk about it exactly right now. Why not? We got some extra time, I think, right now. So P bar equals alpha P bar plus 1 minus alpha E transpose over N. This E vector is something that is used throughout the paper a lot. It is the vector of all ones. E is the vector of all ones. And so that implies that E transpose, the outer product of the vector of all ones with itself, is the matrix of all ones, and then you divide by N, and so that's the matrix of E transpose over N. And our 3 by 3 case is 1/3 of 1, 1, 1, 1, 1, 1, 1, 1, 1. And the point of doing this little transformation right here, the point of doing this transformation, again, is to make things irreducible. This is a very obviously irreducible matrix because if we, you can go from anywhere to anywhere else. So it's somehow obviously irreducible. And by mixing our previous matrix with this like maximally irreducible matrix, we're guaranteed that P bar bar will be irreducible. So that's why we do this. After doing this formula, our P bar bar, let's see, I'm going over a lot of space right here. Our P bar bar will look like so the bottom 3 rows totally unchanged, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, and the top row will be alpha minus 1/3 alpha, 1/3 I'm just trying to think. So this top row, where it's coming from is, but the reason all these bottom rows stay as 1/3 is because our right-hand side over here, E transpose divided by N, that's 1/3 everywhere in the bottom 3 rows. And P bar itself is 1/3 in the bottom 3 rows. So mixing those two matrices together, taking a linear combination of those two matrices, doesn't matter what these weights of alpha are right here, you're going to stay as 1/3 in all these combinations. This top location, though, it's so this alpha times 1 right here, minus 1 minus alpha, 1/3. There's a lot of space. So alpha minus 1 minus alpha, 1/3. This one right here, both of these two spots equal to 1 minus alpha times 1/3. The concrete numbers right there, not super important, but I wrote them out to make maybe make it more concrete what exactly this definition is doing. Last step here, though, the reason I did all of this is because we're, again, going back to the rank of this matrix, and we want to know, is the rank of P equal to 1 or not equal to 1? Either prove it or give a counterexample of this fact. And here we have just constructed a P bar bar matrix where the rank is not equal to 1. In this case, I know by inspection that the rank of P bar bar is equal to 2. How do I know by inspection that the rank is equal to 2? Well, one of the properties of the rank of a matrix is the number of linear independent rows of that matrix. Here, these two rows right here are linearly dependent on each other because they are the same exact row. But this one up here, this first row, is different. And so that's why the rank here is equal to 2. So this first statement up here is false. And that was our counterexample. And similarly, the second statement down here, rank of P bar bar is equal to N. Well, it's the N value here is 3. 2 is not equal to N. So this is also false with the same counterexample. In general, P bar bar can be anything greater than or equal to 1. A lot of steps, a lot of definitions that we went over here. Any questions about any of that? My guess is that everybody actually has lots of questions about this, that none of this made sense to anybody, and that's okay because it was all very fast, and it is hard to follow along with these sorts of things when you are seeing it for the first time, and professors going super fast, and so my recommendation again is that these problems, you can't do these problems. It is impossible to do these problems if you don't know the definitions here. That here we had to apply 3 different definitions, P, P bar, and P bar bar. So that's why I'm forcing you to memorize these definitions for the next class section, is so that we can actually talk about these problems and you can have a chance of following along. You can't follow along if you don't know what the definitions are. And I also recommend actually like trying to sit down and work through as many of these as you can to practice those definitions and understand why things are the way they are. But again, the quiz on Wednesday, you won't have to do any of that. You just have to know the definitions. The quiz is I will print exactly those 2 pages from the workbook here, from the notes, and you will write out those definitions. There is no like applying them or anything at all. It is just strictly memorization and writing them out. Yes.
So for the rank, is it 2 because the second and third row are linear?
It's a good question, and the question is for the rank of for the rank of P bar bar right here, the rank is equal to 2 because these 2 rows right here are linearly dependent on each other. And one definition of the rank of a matrix is the total number of rows that are linearly independent of each other. This top row up here is independent of these bottom 2 rows. Again, independence means that there is no linear, there's no way to multiply this by a scalar, this top row up here by a scalar to get this bottom row. But this bottom row, we can multiply, this middle row right here, we can multiply by the scalar of 1 to get this bottom row right here. So these 2 rows are linearly dependent, but these 2 rows are independent. The way to think about dependence and independence is that these 2 rows are like, in this case, they're exactly the same, but they could be like basically the same and be dependent on each other. But if things are independent, then they're like totally different things. So this is usually the most easy way to determine the rank of a matrix is using this definition up here, the number of linearly independent rows of columns. This second definition down here about the number of non-zero eigenvalues. This is usually the nice thing to know, the thing that the reason we want the rank. It's hard to compute this thing down here necessarily, but it's nice to know. And we can compute it not by directly computing eigenvalues, but instead by computing this top thing up here, the number of linearly independent rows and columns. Good question. Yes, Jay?
Was it possible to go quickly how you got the top row of P bar bar?
Yeah, the question is, how did I get this top row of P bar bar? The answer is we have this formula right here for P bar bar. This is the just definition of P bar bar. We haven't gone into yet why it's the definition about P bar bar. The short answer about why this is the definition is that that this is guaranteed to be irreducible. But we'll see why that is the case later on. But here, just like plugging in the numbers here, it gives me this top row up here. What should be plus? This right here should be a question is, yeah, this minus right here, should that be a plus? The answer is yes, it should be a plus. This alpha comes from this alpha right here, this 1 minus alpha 1/3. This comes from 1 minus alpha right here, and the EE transpose being equal to 1/3 in this cell right here. And we're doing the top left corner right here, top left corner, and the equation up here is plus. So that in fact should be a plus. Yes, thank you. And then this 1 minus alpha of 1/3. So both of these right-hand terms, 1 minus alpha 1/3, 1 minus alpha 1/3, come from this 1/3 in the EE transpose over in, the 1 minus alpha coming from the 1 minus alpha over here. It's like 0 plus over here, 0 plus 1 minus alpha, because in the P bar matrix, we have zeros in those 2 terms. So we get 0 or maybe alpha times 0 of that, and it's just the right-hand term because it's zeros in the P bar matrix. We have an alpha over here because there's a 1 in the P bar matrix in this location. Good question. Yeah, difficult to follow along. Possibly impossible to follow along with something like that if you don't just have an obvious, if the definitions are just not instant into your head, fully memorized. Okay, I'm going to pause this notes packet. We just have 5 minutes left. I'm going to pause this notes packet, and I want to do just a really quick minute on the next notes packet over here, this pagerank 2. Again, this is the notes2.pdf file if you're doing things electronically, or if you're doing things on the printed out versions, this is the packet that I passed out today. And so the previous packet, Notes PageRank 1, is all what I'm calling trivial problems, because it's all about just immediately applying the definition and making sure that you understand what a definition is of something. Here, this first set of problems, they're like, I would call them less trivial than the previous problems, because these actually require you to understand more about what PageRank is doing and why. So let's start talking about this problem 1 right here. And I'm not going to read the problem. We're not going to talk about like what the problem's actually asking yet. We're going to talk about what this PageRank model is or the random surfer model of PageRank. And that's what will be the useful tool for solving problem 1 right here. In order to talk about that, I'm going to go over here to this reading again and use their figure 1 right here to talk about the random surfer model of PageRank. And this again is the location in the reading where they are talking about the random surfer. The idea of the random surfer model model is that if you are a random person in the real world, then when you first visit a web page, we're going to imagine that you just randomly pick a web page off the internet to visit. And so we're going to randomly start here with web page 3. That is our random web page that we just immediately start to visit. And then each of these links, we're going to randomly click on a different link in the web page in order to in our web browsing session. So I might first go to web page 2, following that link, and then while I'm at page 2, go to page 1, and then on page 1 I might click another link that goes back to 3, and then at 3 I might click another link that goes to 5. So here, all of these links right here in blue, this is a measure of my current session on the web. This is my session on the web. And after eventually I'm done surfing, I might come back to a different web page or go start a new web surfing session. And this time maybe I'll start at 6 and then go to 4 and then go to 5. And then 5 has no links anywhere up here. So from 5, I might then go back to 4 and then back to 5 again, bouncing around from between those websites. And so this is a different session on the web. The idea of PageRank is that if we simulate doing this with an infinite number of people, starting in random locations and randomly going to different spots, then our PageRank vector, which is pi, again, one of the things that you'll have to have memorized its definition, pi is the probability distribution that this random surfer is going to land on a web page. Pi is the distribution or the probability that somebody will be on a web page. Distribution of the surfer on a web page. Oops. And this is the thing that we're going to actually be calculating with PageRank. This pi is the thing that we're going to be calculating with PageRank. And those purposes of those first conceptual problems that we'll do get started with next time is to understand why this is a good representation of the importance of a web page. This is a good spot for us to stop for today, though. Again, quiz Wednesday, definitions. You will also do much better following along in class if you have a good read through of definitely section 3.1 here, but as much of the rest as you can as well. If anybody has more questions, we'll stick around to get those answered. And I also have the office hours again, Tuesday, Thursday, 9 to 11 a.m. But that is it for today.